Okay, so let me move the last speaker in the afternoon session, the Professor Sung-Yoon Chung. Professor Sung-Yoon Chung received his PhD degree from KAIST and conducted the postdoc at MIT in Professor Yan-Ming Chiang's group. Then he has worked as a principal editor of Journal of Materials Research since 2016. His research interests encompass materials physics and chemistry of complex oxide for electrocatalysis and nanostructure control of materials interface. Please welcome Professor Sung-Yoon Chung.
Okay, thank you for the nice introduction. As I am Sung-Yoon Chung, working at the KAIST in the Department of Material Science, and thank you again for the nice invitation for this symposium to Professor to give. So today's talk is about the correlation between the local crystal structure and electronic state for high activity and durability of the complex oxide catalyst. Basically, my talk will be focusing on the oxygen evolution reaction catalyst today. So as you can see in this slide, to obtain the high hydrogen green fuel, we need water splitting. So at the cathode side, we can observe the high hydrogen evolution, and also at the another side, we can also observe the oxygen evolution. So maybe as discussed later, the oxygen evolution, the overpotential much higher. And the second example is the fuel cell. So as you can see in the cathode side, there's a huge voltage drop based on the well-known the cathode activation loss. So this is why we need a platinum-based catalyst to improve the oxygen reduction reaction. So, and also the third case is maybe you can see the previous presentation by Jun Lu from the Argonne National Lab. So metal air battery, we need a charge and discharge. So increase the efficiency of the round trip efficiency, we need a catalyst in the anode and cathode to induce reduce the charging and discharging over potential. So I think the oxygen evolution and reduction reactions the key electrochemical reaction in many electron and energy conversion and storage devices. I think this is a typical polarization curve. As you can see in this curve, compared to the hydrogen evolution at the cathode side, you can see much more higher over potential because the 4 electron, okay, the 4 electron reaction is very necessary to evolve the oxygen at the anode side. In principle, you know, the theoretical potential for the oxygen evolution is 1.23 volt, but the activation barrier is pretty high, so we need a much higher voltage to drive the oxygen evolution reaction at the anode side. So what we need is the water electrolysis is this hydrogen evolution at cathode, and the oxygen evolution is the anode side. Okay, so as you can see in this slide, basically the oxygen evolution is based on the 4 electron. Okay, the 4 electron engagement is necessary. So that's why the bottleneck, okay, to obtain the hydrogen gas by using the water splitting, the bottleneck reaction is on the anode side. So that's why we need an efficient OEL electrocatalyst. In the earlier stage, actually, the first generation descriptor is based on the bond ranks of the intermediate species, such as OH or OOH. So as you can see in this graph, you know, in principle, there's a 4 step, okay? 4 electron reaction is based on this 4 step of the reaction. So each step as you can see in this slide, this is an ideal case. So each step is a 1.2 volt. So that is the ideal case. That I think this is the perfect electrocatalysis for the oxygen evolution. But in some steps, if the larger than 1.23 volt, we call this a rate limiting step. That is much efficiency is much lower than the ideal step. So that means is we need a larger potential. Okay, with that point, it would be the ideal catalyst. So, but in this case, the second step is much more than 1.23 volts. So that means this is a rate limiting step. So that means the overpotential. Okay, the potential of the OER is much higher. So what we need is the low overpotential is the ideal case. Okay, that means that is maybe the best OER catalyst. For example, the stream cobalt oxide is very close to this ideal case. Okay, since the 2011, so many researchers have been focusing on the electronic state, okay, to improve or to discover a new material for the OER catalyst. So since this 2011, I think in this literature, this is EG1 electron principle has been suggested. Okay. Lower than 1 electron, the bonding state is too low, so weak bonding between the OH and M site, and that is a two weak bond and strong bonding. So best is intermediate bonding state is a best. Okay. So second, in 2013, it's an oxygen 2p band. The model has been suggested. Okay. If the oxygen 2p band and the metal is overlapping, there is a much higher, much more efficient charge transfer can be achieved. So oxygen 2p band is close to the Fermi energy level, such an overpotential is much lower. Okay, so that means that would be the best OER catalyst in this series of the ruthenium cobalt oxide. Okay. And then in 2017, there's also charge transfer mechanism has been suggested. As you can see, the charge transfer between the oxygen 2p and higher metal 3D, that the smaller, okay, the smaller charge transfer means the higher activity of the during the electrocatalysis for the oxygen evolution. Okay. In 2017, will be discussed later in more detail. We have been focusing on the density of state, including such a charge transfer concept. If we have as a larger density of state near the Fermi energy level, that can be give more whole state. Okay, after and when the applied voltage at the anode side, such a Fermi energy level will be lower. So if we have some large state of the near the Fermi energy level, that can be a lot of room for an electron hole. So which means it's very efficient to the oxygen evolution reaction. So what we have been focusing on the density of state beneath the electron Fermi energy level. So I think it's quite consistent with the recent report by the Nong published in 2020. Actually, you know, at the anode side, there is strong oxidizing atmosphere is expected. So the oxide structure, okay, as you can see in this slide, the oxide structure is basically the oxygen octahedra, including some small cation in this intercept site. So we can control the local structure. So that means the electronic state will be huge difference, okay, between the oxygen 2p and the transition metal 3D, and a strong correlation. So what we need is the crystal structure. Okay, the first step is crystal structure variation. So which means because such a crystal structure variation, so always result in the difference electronic state. Okay, so to control the catalytic property, we need to understand the crystal structure and electronic state at the same time. So that's why we need a direct observation to understand the variation of the crystal structure in detail. Okay. So I think maybe more than 10 years, so over the last 10 years, we have been using some scanning transmission electron microscope to observe the detail of the crystal structure, especially in the oxide material, because the oxide is basically the FCC oxygen framework together with the cation, the many different cation at the intershell site, including the tetrahedral site and octahedral site. So I think the STEM observation is very essential to study the oxide material. So we have been using maybe more than 5 different TEM, including the one major Titan at KAIST. This is the major TEM facility. So we also use some different type of Titan in the Eindhoven in the Holland. So this is another imaging correction. Okay, this is not basically the STEM, just the TEM. So Vibra is another type of TEM we have been using for a long time. And this is a high voltage. It's more than the acceleration voltage is more than 1 megavolt. So it's very efficient to the high temperature. Okay, the high temperature AC to TEM. And we also use the FIB for oxide ion beam facility to prepare our sample, because we have our sample. Some of our sample is basically the thin film. So I think the FA focused ion beam is very necessary to prepare our sample more efficiently. Okay, the STEM. Okay, STEM is a little different from just conventional TEM. In the just conventional TEM, we use the parallel electron beam. Okay, but instead of using the parallel electron beam in the scanning transmission electron microscope, we use a convergent Ångström level, very small, tiny electron beam. We just scan the electron beam on the in the sample, okay, in the specimen, so we can acquire the scattered electron in the bottom. Okay, so when we use some large scattered angle at a large angle, for example, more than 70 millirad, so we call this high angle. Okay, just high angle annular dark field. In this mode, basically this mode is called as a Z contrast imaging mode, because it's the atomic number, the atomic intensity in the image is proportional to the atomic number of the Z number. So I think this is quite a good example. This is the lithium cobalt oxide. I think maybe the Jong-Min Wang has presented his talk is very beautifully. So you can see the lithium cobalt oxide is composed of the lithium. Okay, the atomic number is highest in this material. The oxygen and lithium is very light. So I think the atomic number of lithium is just 3. So this cannot be imaged in this mode. So only the lithium, okay, the bright one is only the lithium color. So without visualization of the oxygen and lithium. But in this STEM mode, we call this annular bright field. Okay, such an acceptance acquired angle is much smaller. It's between 11 and 22 millirad. So scattered acceptance angle is very small in this case. In this mode, we can visualize the light element, including the oxygen, lithium, and even the hydrogen is possible. Okay, this is an example. The barium zirconate perovskite material, oxide material. So in indium doped barium, indium is accepted in the lattice. There are so many oxygen vacancies should be observed. So by using this ABF, we could visualize such a last dark. Okay, so last dark oxygen column could be visualized, which means this is an oxygen vacancies. Okay. I think this is another good example to show the powerful tool of the ABF. This is a vanadium pentoxide, which is hydrate the zinc ion intercalated in the vanadium pentoxide. This is a pre-seen vanadium oxide. This is a typical layer structure. So in this high angle and a dark field, there's only the vanadium column should be visible, okay, right? But in this ABF, you can see the oxygen side also can be observed. So in the second example is the hydration zinc intercalation, which means the zinc intercalation together with the water molecule. So you can see there's no contrast at all. But in ABF, you can see the black contrast in the M1 side, which means that is the water, okay, H2O. So the overall Z number is very low. So in this mode, this cannot be imaged. But in the ABF, you can see very clearly the presence of water molecule in the interstitial site. Okay, this is another good example, okay, observed by the Young Jae-hong and Phil Gubian in our group. We have observed so many different layer type oxide material. Okay, in this strontium titanate and lanthanum nickel, that is a lanthanum cobalt. In this case, the oxygen. Okay, the oxygen octahedral is almost the cubic, almost diamond cubic position. But in this case, you can see the oxygen is elongated along the z-axis. So strong elongation oxygen octahedral can be observed by using the AFM. The third case is a copper. Okay, the copper is much stronger elongation, very strong elongation could be observed by using. So without such an ABF image, such an oxygen position, this cannot be observed. So I think this is ABF is one of the powerful tools to observe the whole, okay, including the light element. The whole element can be observed. So in this talk, today I will focusing on the oxygen evolution oxide-based catalyst. The part one is for higher. Okay, the part one is high activity of the oxygen evolution electrocatalysis, focusing on the local crystal structure and the electronic state correlation. And part two, I will briefly mention the durability. Okay, the high activity does not guarantee the high durability of the catalyst. So part two, I will briefly mention of the strong correlation between the crystal structure and the catalytic durability. So part one is symmetry. So most of the content will be about the symmetry breaking a local structure for the high activity. As I mentioned, the density state, electronic state, okay, the density state beneath the Fermi energy level is pretty important to improve the activity of the oxide material for the oxygen evolution reaction. So we carried out some model experiment using the epitaxial thin film. Instead of using some nanoparticle, we just focused on the utilization of the heterogeneous lanthanum nickel film, because the nanoparticle has so many different facets. So we cannot understand which one is much more higher, to which one is much lower activity. So we use such a heteroepitaxial thin film. So that means the surface, okay, the surface is always at the 001 crystallographic surface, okay, and basically the Beijing material is lanthanum nickel oxide. It's a metallic material. So by using some different type of dopant, including the iron, cobalt, aluminum, and scandium, so we can examine the effect of the composition, because the thin film is basically the same. The different thing is only the dopant. Okay, so by using such an experiment, we could examine the effect of the dopant composition. Okay. So as you can see, the thin film, okay, thin film fabrication is very successful, and the surface is very clean without any secondary phase. And also we also carried out the depth calculation by using such a DFT calculation, I think this calculation is much more straightforward because the crystallographic plane is always the same. Okay, it's very precisely controlled by using some supercell. Okay, so through this calculation, we can identify that iron. Okay? As you can see, the iron and cobalt and chromium has a strong densive state near the ferroenergy level. So, but in contrast, the aluminum and scandium and manganese and indium, there is no densive state near the ferroenergy level. Okay, by doing some direct measurement for the OEL activity, we can observe very consistent result. As you can see in this graph, the iron, that is a pretty sample. The activity of the iron, the cobalt, and chromium doped sample is more than twofold higher activity that of the present ruthenium nickel sample. But you can see the scandium, manganese, indium doped samples, the activity is almost the same with that of the present ruthenium nickel oxide. So you know what, this is a very nice example to explain the correlation between the density of the state and the composition and activity. Okay. So as you can see, you know, the cobalt is one of the best composition because the high intensity, okay, high density of the state is near the ferroenergy level. So the second experiment, we just prepared the solid solution between the ruthenium nickel and ruthenium cobalt oxide. Okay, we could fabricate complete solid solution between the two end members. So by measuring the OER activity, we could also observe the strong correlation, almost a linear correlation between the ruthenium nickel and ruthenium cobalt activity. I think the ruthenium cobalt the activity, okay, OER, the catalytic activity is ruthenium cobalt oxide is more than 1 order higher of the ruthenium nickel oxide. So I think the density state and the relationship of the density of state and the composition is quite straightforward. Second example is the crystal structure observation. Okay, in this example, actually this study is triggered our study of the ruthenium nickel thin film. So when we fabricate the thin film by using the sol gel process, there's two different type of thin film could be observed. The one is the nickel excess. It has a perfect clean crystal structure. Perovskite, that's a perfect perovskite structure. But when we add some ruthenium excess, the 1 or 2% ruthenium excess sample, as you can see in this image, there's so many Rotherstand Popper, okay, two-dimensional defect, ruthenium consecutive defect could be observed. Okay, so by using some ABF-TEM, okay, we could also identify the oxygen distortion. Oxygen elongation is easily observed by this ABF image. That is a bulk type, so it's almost cubic. Okay, pseudo-cubic structure is a very well-known cubic structure, but at this fold state, okay, the two-dimensional fold in plane, you can see the oxygen. Okay, that oxygen is elongated downward, so which means it's a strong distortion of oxygen octahedra. Okay. So by using the DFT calculation, we also identify the different density of state is obtained. So this is the bulk type density of state, but in the fold plane, you know, in the by such a strong elongation of oxygen, you can see a lot of much more higher rise of the oxygen 2p and nickel 3d near the ferroenergy level. So this means such a fall is much more sensitive or much more higher activity for the oxygen evolution reaction. By measuring such a two different sample, okay, the blue one is the perfect clean without the false sample. the yellow is a lot of such a defect samples. So as can be seen in this graph, the activity of the oxygen divergence is twofold higher. So that means, such a defect is much more active side for the oxygen evolution reaction. Actually, this is the first example to focus on the defect size as an active OER catalyst. The second example is the grain boundary, because the grain boundary is a well-known symmetry broken atomic site, right? So we examine the effectiveness of the grain boundary. We prepare the polycrystalline sample, okay, by sintering the powder. So sample A is a fine grains polycrystalline sinter sample. So that means the grain boundary, the area, okay, the grain boundary length is much more higher. But in the sample C, as you can see, it's a larger grain sample, so which means it's grain boundary. Okay, the length of grain boundary much shorter. So what we expected is such an activity. Okay, OER current density should be higher for the sample A compared to that of the sample C. So that is a measurement result. That is exactly the same of what have we expected. So as you can see that the activity of the sample A is much higher. So we have three samples, but by using the two sample, by solving the simultaneous equation, because unknown the current, the activity of grain and activity of grain boundary, we have just two unknown, but we have two equations, so we can obtain the solution, okay, by solving the simultaneous equation. Okay, based on this equation, we could identify that the grain boundary, the activity of grain boundary is more than 80-fold higher than just a simple surface of the grain. Okay, so grain boundary. So based on this result, it is very clear that the grain boundary is much more active site for the oxygen evolution reaction electrocatalysis. So to confirm, okay, to confirm the effect of the grain boundary, we carried out another model experiment by using the bicrystal substrate. Okay, this is a bicrystal, means such a crystal contact, because basically that is a two crystal, and this is one single grain boundary is obtained by using some bicrystal. Okay, the strontium titanate bicrystal, I think it's commercially available. So by using such a strontium bicrystal substrate, we fabricate the ruthenium cobalt thin film using this substrate. So that means, we have only one single grain boundary of the ruthenium cobalt oxide. So by applying such a mask, epoxy mask, we measure one single grain boundary for the OER catalyst. So this is a result. Okay, the black curve is without such a simple, okay, simple single crystal ruthenium cobalt oxide. The red one is the bicrystal, okay, the sample containing the one single grain boundary. So activity, some people say that the activity is so small, but it is not that small, because the width of grain boundary is a nanoscale, as you can see. Okay, so compared to the small width, the activity enhancement is so huge. Okay? So by using some TEM observation, we also confirm that the site of the cobalt, including the oxygen, is very distorted. So strong distortion can be observed at the same time. So we also, I think this message is the same. Okay, the strong distortion can convert or can change the density of state of the material very huge. So it's an active site. Okay, grain boundary is a very active site. Okay, third is this ion incorporation, because the ion is very famous for to improve the activity of the nickel-based oxide. So in this series of experiments, we just exchange of the nickel with iron by using some anodic reaction. Okay, in this case, we use iron-containing electrolyte, okay, for the ion exchange experiment. So this is an ion exchange sample. Okay, by measuring, we identify the activity of the ion is so huge. It's more than 1 order higher. The huge increasement can be observed by the ion exchange ruthenium nickel oxide sample. I think the message is the same. Okay, by using some ABF images at the surface, okay, ion exchange at the surface, there's a strong distortion. Okay, as you can see, the oxygen, that is a nickel and iron. The strong distortion is a common feature during our observation. I think this is IDPC. This is another imaging technique to enhance the contrast of the oxygen. So at the surface, you can see a lot of distortion, a lot of displacement of the oxygen could be imaged in this sample. Okay, I think this is another consistent series of image. So density state, the very constant result can be observed. As you can see in this graph, there's a strong rise of the iron and nickel can be observed. So local structure control, okay, to increase the OEL activity, I think the local structure control is very efficient. The tool in the oxide, in the complex oxide material. This is the last example. Yeah, you know, the crystal structure. Okay? Basically, our sample is a crystalline material, but if the sample material is amorphous, such a distortion is not always beneficial because the amorphous state, there is no specific crystal structure. So this is our series of another experiment to show the crystallinity or the state of the sample is important. By control the temperature, we could observe we could obtain the amorphous sample instead of the crystalline sample. Okay, at the lower temperature, this is basically the amorphous. Okay, at the higher temperature, we the consistent the crystalline sample. So two different samples can be compared, right? So I think the ion exchange is exactly the same, but the amorphous sample, so activity enhancement is very negligible. So which means is such a strong distortion has no effect in the amorphous sample. So which means it's crystalline structure control, okay, is beneficial for the crystalline case. So ABF is the same message in the pristine, that is ion exchange. So strong distortion is always consistently observed, and compared to the solid solution, which is equilibrium state, such an ion exchange is strong distortion because the composition would be the same. The strong distortion is always very exceptional activity shown in this series of example. So the crystal structure and has a very strong correlation to the variation of the electronic state. So I think it's one of the great opportunity to discover another set of the new catalyst. I think it's time is not that sufficient. So part 2, I'm gonna briefly mention of the part 2, the catalytic durability. Okay. So in the acid, you know, this is a second generation of the PEM. That's a proton exchange membrane-based electrolysis. In this configuration, this membrane, the naphthalene has a lot of proton ion. So that means it's overall environment in the cathode and anode, I think that's it. The overall environment is really acidic. So only one, okay, in the Oxide side, maybe the iridium-based oxide is the best catalyst material, because the most of transition metal oxides is dissolved so fast. But in the oxygen, but iridium oxide, even at the low pH, is very stable. The problem is the price. The price is much more expensive than the gold. So reducing the utilization of the iridium at the anode catalyst is one of the key issues in this PEM, proton exchange membrane base. So we investigate different type of complex iridium-based complex oxide. But the interesting thing is most of them is activity much higher. Okay, but the problem is the stability. Okay, as you can see, the barium and calcium iridate, the activity is rather increasing. It's not that bad. But in this case, the barium and strontium iridium oxide, okay, the activity really high. Initial activity is still really high, but such an activity is disappear after only just 20 anodic cycles. So durability is another issue in this complex oxide. So to examine the origin of such a low durability, some alkaline earth iridate oxide, we directly observed the crystal structure after anodic cycle. So as you can see, the huge dissolution. Okay, that is a composition iridium and strontium. The huge dissolution of the strontium is identified. So this is one of the reasons of low durability of the complex structure. The complex oxide is, even though there's initial activity is very high, so it's a typical image showing the strontium after strontium dissolution. The remaining structure is iridium-based oxide nanocrystal. Okay, so high activity is based on the high surface area, based on the dissolution of the strontium. So we examined all the 11 iridate. Okay, we just investigate all the crystal structure of the 11 iridates. So we could categorize the 3 different groups. The first one based on the connectivity between the iridium 06 oxygen octahedrite. Okay, that is the single unit of the iridium 06. So group A is basically the phase shear connectivity can be observed. So which means it's very strong. Okay, the connectivity between the iridium 06 is very strong. Okay, but group B is corner shear. Basically, this is a one phase shear connectivity, but basically the other 2 is corner shear. So connectivity is just intermediate. But group C, as you can see in the calcium and strontium iridate, there's no connectivity at all, right? So which means it's after such a calcium and strontium dissolution, there's no connection at all. So that means the strong collapse. Okay? Strong collapse is anticipated after calcium and strontium dissolution. I think what we expect is exactly the same with the measurement of the group A. Okay, the activity does not diminish at all. It's rather increase. Okay, and group B, the activity is not that bad. Okay, after a lot of anodic cycle. But group C, the activity is huge diminish, which means the lattice is rapidly collapsed after the barium and strontium and calcium dissolution. Okay. So group A, even if the barium and the calcium dissolution cannot be avoided, but their connectivity is very high. So the remaining oxygen, iridium oxygen connection is still preserved. So that's why there's a durability is very high. But the group C, as you can see in this schematic diagram, there's a very rapid collapse, cannot be avoided. So you can see in this EDS mapping, there's a small remaining strontium is observed. So the other part is strontium is almost gone. Okay, so that's why the crystal structure is very important to decide the durability of the complex iridium oxide. Okay, So today's talk is mostly the part one. We just focusing on the correlation between the local structure, crystal structure, and electronic state to achieve the high activity. And part one, we just briefly mentioned the crystal structure important and the feature of the crystal the structure for the catalytic the durability. Okay. So finally I would like to thank all our team, including the former PhD and MS and postdoc student. Okay, thank you.
Thank you very much for the impressive presentation. Now time is open for question. We have many questions. So
how many questions?
now I think it's a 6. So the first question, thanks for the wonderful lecture. I have a question on the elongation on oxygen atom. Is the orientation of oxygen elongation could be controlled? If the orientation of oxygen changed, would the catalytic property changed or tuned?
Okay, I think that's a good question because it is for the ion exchange, it is just random. Okay, the oxygen octahedral distortion is because it's just an exchange carried out at room temperature. So basically, at this stage, we cannot control the oxygen distortion. That's why we just, we consider all the possible distortion by using the DF calculation. Okay, yeah, that's the limitation of the oxygen distortion approach.
Okay, so second question. Thank you for providing us with many beautiful examples of advanced TM analysis. Do you have any comment or recommendation for those wanting to investigate high entropy oxide for studying their mechanism for their catalytic activity?
Oh yeah, because the high entropy means the different composition atoms. So many different composition atoms is included in one single sample, right? So it's really complex. By using the TM now as a state over not TM, you can identify or you can distinguish which atom is which. But I think it's still challenging to identify the correlation between the composition and structure because so many composition combination. Okay, so I think this is another good topic for the electrocatalysis.
Yeah. Okay, thank you. Next question. Thank you for the great talk. Is the distortion of oxygen octahedron always induce a generation of DOS of O2P near Fermi level? What is the main reason to determine the position of newly generate DOS of oxygen 2P when oxygen octahedron is distorted?
Yeah, I think it's the question is basically the same as the comment of the review of when we submit the paper. Actually, the distortion is all not. I cannot say distortion is always beneficial to change the density state, because but it's just a trend because the Jahn-Teller distortion. You can consider the Jahn-Teller distortion, right? I think it's briefly. Maybe time is up. Yeah, this is a Jahn-Teller distortion, right? Some kind of degeneration is removed by using some distortion. So that means the electronic state, okay, the DZ state or the x square minus square is a little lower, and your distribution, okay, energy level of distribution is much more not discrete. So that's why we can obtain the higher energy state near the Fermi energy level. So it is not always. Okay, that's the point.
Okay, thank you. Another question. I wonder if dislocation induced elongation could also induce the changes in catalytic performance.
You mean the dislocation?
Yes.
Just a one-dimensional defect?
Yes.
Yeah, the Professor Matthew Matthew Kahn group at Stanford, they report the paper in Science this year or last year, showing that dislocation is effective, maybe the CO2 reduction, I think, but I'm not sure. We also try some similar experiment by using dislocation introduction, but I think it's a little effective, but it's not as effective as a grain boundary.
Okay. Next question. I would like to ask the potential of future, the research direction for developing electrocatalyst, which is majority based on the non-precious metal. So, do you have some comment on the future, the research direction?
I think current direction, one of the big challenging of the current direction is, I think the high activity is also important, but current direction is durability. Okay, stability of the catalytic activity, because as you can see in the last part too, the initial high activity is should be preserved for a long time. So current direction, one of the big direction is to achieve the durability rather than the high activity. Yeah, that's the atmosphere in this field.
Okay, so another question. You introduced the lanthanum cobalt oxide, the solid state reaction, the sintered, the oxygen evolution catalyst. And you told me the 85, the ePold, the enhancement in the catalytic activity. Is it possible to maintain exceptionally high the grain boundary, the density for the further improve the OER? The activity?
I think the crystal preservation of the crystal structure is not an issue, but an activity, okay? The degradation activity is very difficult to avoid for a long time, anodic cycling. That's the issue, yeah. So I don't think 85-fold higher activity is preserved for a long time. I don't think so.
Okay, so we still have the several questions, but due to the limited time, and I would like to ask the last question for you.
Okay.
How to bridge the gaps between the fundamental research and the industrial, the application for the water, the electrolysis?
In the industrial application, we need to consider much more factor, including the price and manufacturing capacity, including the activity and durability. That's the point. So I think the fundamental study should provide such an insight, okay, to the industry application.
Okay.
Yeah.
Thank you, Professor Chung, again.
Okay. Thanks so much.